Hello, welcome to this lesson in the Laplace transform tutor. Here we're finally going to begin to use the Laplace transform for something useful. When I put together this course, I have to decide how to convey to you how these things are useful. The truth is Laplace transform is used for all manner of different types of problems, whether it be chemical engineering, electrical engineering, mechanical engineering, pure mathematics, physics. It really just comes up all the time as a very useful thing. But the one thing that you can kind of call a unifying feature of why it's useful to so many different branches of math and science and engineering is because Laplace transforms can be used, and we've said it before, to solve differential equations, in many cases faster and easier than the methods that we learned when you learned differential equations. If you remember back to your differential equations course, there are many solution techniques and they all depend on the exact type of equation you have. And so you have to learn a lot of different techniques and so on. Here we've spent a lot of time in the last 6 or 7 sections or whatever it is, building a lot of overhead and teaching you what a Laplace transform is, how to take the transforms, and how to do the inverse transforms. And we certainly have not explored all types of Laplace transforms, but we have constructed a table of very common functions that you see pop up in real life. You'll see these pop up a lot of times in engineering problems and science problems, and it turns out that what's on the board here, in addition to what we'll learn coming up, really can let you solve a wide array of really practical problems. All right, so what we're going to do is we're going to solve some differential equations, and this is not necessarily a course in differential equations, but it illustrates to you why the method and why the transform is so important. So as we solve this differential equation, and as we go off and solve the differential equations in the sections that follow, just try to keep in mind that that's really my motivation for teaching you why it's important. Because although this differential equation might be trivial, or the next one in the next section might be, an equation you might not ever use, when you're in a physics course, or whenever you're in a mechanical engineering course, or when you're in an electric circuits course or something, you may have a differential equation that may very well look like one of these with different constants, or it may be of the same type or a similar type that you can use Laplace transform methods to solve much, much easier than you would if you have to go back and dig through your notes for differential equations. So, saying all of that, if you remember back to what the concept of a differential equation is, basically an equation that has derivatives in it, right? It's an equation where whatever you're trying to solve is a little harder to get at because it's wrapped up inside of a derivative, right? So it leads to lots of different solution techniques. So what we're going to do as a general big picture is what we're going to do is we're going to take the Laplace transform of our differential equation. We're going to take the Laplace transform of both sides. Remember, you can do anything you want to an equation as long as you do it to both sides. And since we have demonstrated that the Laplace transform is a reversible transformation from t domain to s domain and back to t domain, you can apply it to both sides as an operator to both sides of your differential equation. That will transform the equation. It's something that looks different, but we hope it's easier to solve that way, and you'll find out that it is. And when we get our answer in terms of s domain, we now invert it back to the time domain. That's what we're really trying to do, so keep that in mind. But before we can actually apply that method, you need to know how to handle when you apply a Laplace transform to a derivative, because every differential equation has to have a derivative. We have never talked about how to apply differential equations, or I should say how to apply Laplace transforms to any sort of derivative. We haven't talked about that. So before we can solve an equation, we need to figure out how Laplace transforms and derivatives work. So having talked about that here, what we're really trying to say is, remember, a derivative can be written in several ways. It can be written as x prime of t. This means the derivative of x with respect to time, x being a function of time. So if we're doing a Laplace transform of this particular term, we might be applying the Laplace transform to x prime of t. This is going to be exactly the same thing as if we had tried to apply it to something called dx dt. Right? This is just notation. So sometimes you might see your derivative written as x prime of t. Sometimes you might see your derivative written as dx dt. We're just applying the Laplace operator there. And when you take a differential equations course, the derivative frequently is expressed as a capital D operating on the function x of t. So of course you can have a Laplace transform applied to that as well. As we work a lot of our differential equations, we're going to see this a lot because that's typically what we see when we do differential equations, but just keep in mind, when you see a capital D, it just means derivative. If you see a d squared, it means second derivative. If you see a double prime, it means second derivative, and so on. It's just notation I'm kind of going through here. All right? So if we were going to try to figure out how this Laplace transform works with these derivatives, then what we probably would do, let me switch colors, if I were going to actually derive it for you here, is I would say, okay, Laplace transform of x prime of t, let's say, which is the derivative, I would just literally stick this function into the Laplace transform, 0 to infinity e to the minus st, and then my function of time is now a derivative, x prime of t dt. So this is literally, if I'm taking a Laplace transform of a derivative, I just simply take that function and stick it into the same spot that we always use. We put our function in here, it's just that now it's a derivative. So what we would do if we were going to derive this is we'd go through the motions and trying to figure out what this is equal to. And I think I told you early on in the course that sometimes I'm going to spend some time deriving things because I think they could really benefit you. We've done that. We've derived a lot of these things from this integral. A lot of these basic transforms on the board we've derived using the integral. I think that's worth our time. I think this maybe could be worth our time, but in this case I don't think I'm going to do that because ultimately it's not something you're going to do. You're going to basically use the result a lot, but you're never going to do this very often. You're never going to basically take a derivative and stick it in there and get the answer. So I don't think it's really worth our time. But ultimately, if we were going to do this, we'd solve the integral and we'd plug in the limits of integration, and that would be how Laplace operates on a derivative. So basically, you would use integration by parts. You would set part of this integral to u. You would set the other part of the integral to dv. You would do uv minus integral v du. You would apply the limits of integration. And what you would get is what I'm going to write on the board right here. And actually, instead of writing it here, I'm going to write it down below our table of Laplace transforms because I want to leave it up there so that we have it as a reference as we go forward solving problems. So what I'm going to do is I'm going to come over here and I'm going to say that this is called the differentiation property. Differentiation property of Laplace transforms. And basically what it boils down to is if you have, I'm trying to decide, let me go and switch colors. Sometimes I like to break the board up with colors. If you have a Laplace transform operating on a first derivative of time, like this, right? Then notation-wise, I'm just going to write it out for you. It's exactly the same thing as the Laplace transforming with a capital D operating on x of t. This is how you would see a derivative written in differential equations, so I'm kind of refreshing your memory on that. When you see this, okay, then this is what it's equal to. S times the Laplace transform of x of t minus x at 0. This is what it's equal to. So whenever you have a first derivative in a differential equation and you apply a Laplace transform to it, it's a single s. By the way, it's a single s because it's a first derivative. We'll see what happens when you have higher derivatives in a moment. Single s times Laplace transform of the function I'm trying to solve minus the function itself, x, evaluated at 0. Evaluated at 0. Notice that this x of 0 is basically an initial condition. If you remember back to differential equations, you have the differential equation you're trying to solve, and then you almost always have an initial condition. What's happening at time 0, or what's happening at time 1, or what's happening at time 5, or whatever, but it's an initial condition of the system. When you specify your differential equation, and you specify enough initial conditions, you can lock down the solution to the real function x of t, which is what we're trying to find. Now, I'm not going to derive how this pops out, right? Because I already said I don't think it's worth our time to do it. However, notice that we're doing an integral of these guys, and if you do integration by parts, eventually you're going to end up integrating this x prime of t, and so what happens is you're going to end up getting x of t, and you're evaluating at infinity and you're evaluating at 0. So when you integrate this and you end up with x of t evaluating at 0, that's where this basically pops up from. That's why the initial condition pops up, is because we're end up integrating that derivative at some point along the integration by parts process, evaluating at that lower limit of integration, and it sticks around. Now, how the s pops out and all that, that would be deep in the details of the proof. I'm not going to do that for you right now. I don't think it's worth it. I think it's a better use of our time if we just learn how to use the result. All right, so what if you have a second derivative? Because of course, many times we're solving differential equations, we're going to have a second derivative. So that might be written as x double prime of t, which in terms of a differential equation, you usually see it as d squared x. That means second derivative operating on x. And what this is equal to is, let me write it down and we'll talk about it, s squared Laplace transform of x of t. Okay, and then you have minus s x at 0 minus x prime at 0. So notice the pattern here. There is a pattern that's beginning to develop, and you may not totally see it yet, but when it's a first derivative, right, you have a single s times the Laplace transform of x minus the initial condition. When it's a second derivative, notice the 2 up here, you get an s squared times the Laplace transform. Notice this is not squared, it's just times the Laplace transform, minus s at the initial condition, times the initial condition, minus x prime at the initial condition. Now I'm going to write the third one down before I really generalize, because I want to make sure you know. If I have the Laplace transform of d cubed, which is the third derivative, which will get you through most differential equations, then what you're going to have is s cubed Laplace transform x of t like that, and then you're going to have minus s squared x evaluated at 0 minus s first power of x at x prime of 0, and then you're going to have x double prime at 0. All right, make sure you understand that. I know this is a lot of junk on the board. Most differential equations books or Laplace transforms books give you a single formula to generalize this. And that formula is a generalization, so it could be any nth derivative. But in reality, when you're solving most problems, you're not going to have a fifth derivative. Most differential equations don't have a fifth derivative or a sixth derivative or a 10th derivative. So it's not very useful to learn how to handle it when you do that. But most equations have at least first derivative. Many of them have a second derivative, and occasionally you'll have a third derivative. So really, what I have on the board is going to get you by on most problems that you'll ever encounter. All right. If you have to go to a fourth derivative or a fifth derivative, you just look at the pattern that's developing here. So let's go over that now. Notice that if it's a first derivative, it's s times the Laplace transform minus the initial condition. The initial condition always starts at x of 0. Okay. If it's a second derivative, it's s squared times the Laplace minus s times the initial condition minus the first derivative initial condition. If it's third derivative, it's s cubed times the Laplace transform minus x squared times the initial condition minus s times the first derivative minus the second derivative. So you can see what's happening. As you go up in derivatives, you have an s cubed, s squared, s, and this is just s to the 0, which is 1, which means it disappears. And then simultaneously, you have x of 0, x prime of 0, x double prime of 0. So in the Laplace transform that pops up here, there's no power on it or anything. It's always just by itself. So if you had a fourth derivative, then what you would have is an s to the fourth times Laplace transform. The minuses are always here. It's always minus, notice that. So you have an s to the fourth Laplace transform. Then you would have minus s to the third times this, minus s squared times this, minus s to the first power times this, and then you have another term which would be x triple prime of 0. So you have to notice that as you go up in the derivatives, first derivative only involves this initial condition. Second derivative involves 2 initial conditions with the function and its derivative. Third derivative involves 3 initial conditions there. And that, by the way, is no accident, all right? When you think about differential equations, right, if you have a first derivative, you only need 1 initial condition to lock it down and solve it. If you have second derivative, you need 2 initial conditions, x of 0 and x prime of 0, to lock it down and solve it, right? If you have a third derivative, you need 3 initial conditions. So the number of initial conditions you need to have always lines up with what the order of the derivative is that you have, the highest derivative you have in your equation. That's why the Laplace transform is very useful, and I'm going to say this a few times because it is very important. Really, that is really why Laplace transform turns out to be so useful. When you take a Laplace transform and operate it on a derivative, then because of the proof that we didn't really go over, basically, what basically happens is when you operate on a derivative, you always get the proper number of initial conditions required to solve the problem in the evaluation of this. That's why it's really useful. because whenever we operate on a derivative, we end up with these initial conditions, which are going to be required to solve the problem. And as we solve our first one here in a minute, you'll see how that becomes useful. Because in order to solve a differential equation, you need to incorporate the initial conditions into your solution. The Laplace transform is incorporating all these initial conditions. And no matter what derivative you take, the proper number of initial conditions is automatically included because that's how it works. All right, so if you have a first derivative, use this guy. If you have a second derivative, use this guy. If you have a third derivative, use this guy. If you have a fourth or a fifth derivative, just follow the same pattern. I think you all can look at that and see what the pattern is. Now what I would like to do is erase the board here, put our first differential equation on the board. I promise it'll be a very simple differential equation because I'm not going to knock your socks off with something super heavy duty to start. I want to put something on the board that everybody can understand, and we'll slowly ratchet up the complexity of everything going on here. So our first differential equation is going to be dx is equal to t, and our initial condition is x of 0 is equal to 2. Now, if it's been a while since you've seen a differential equation, this is an operator notation. So the capital D means first derivative of x. When I say x, x isn't just a variable in terms of these differential equations. It's always x of t. It's a function of time that you're trying to solve for. So that's why we have t's on the right-hand side. So what we have is first derivative of x is equal to this. If I were going to write this in terms of something you might be a little more familiar with, you might see it as x prime of t is equal to t. So this is the same differential equation. This is the way you write it when you start doing a lot of differential equations. This is what you would see more in a Calculus 1 textbook or something like that. So let's work with this, because this is really how you're going to be solving these differential equations. First thing we want to do is notice, I picked this equation on purpose, this is an incredibly simple equation. There's no complication. If you want to look at this part, it's fine as well. You can easily solve this by integrating both sides because it's a function of time, the derivative is a function of time, and there's just a simple t over there. You can actually integrate both sides of this and get the answer. What happens if you do that? If you integrate the right-hand side, what do you get? You integrate t. You're going to get 1/2 t squared plus constant of integration. And when you evaluate your initial condition, you're going to lock down that constant of integration. It's going to be a number. Right? So I'm trying to tell you that this particular equation I'm picking is extremely simple. You can solve it by integration. Most differential equations you cannot solve just by integrating both sides. But this one I'm picking because I want to show you the Laplace transform method. So let's not integrate both sides. Let's instead take the Laplace transform of both sides of this differential equation. So the way you write that is you say Laplace transform dx is equal to the Laplace transform of t. So you literally are taking the Laplace transform of this side and the Laplace transform of the right-hand side. Now we know how to handle it when we take a Laplace transform of a first derivative. We have just written it down here. Laplace transform of a first derivative is s times the Laplace transform minus the initial condition. So what we do is we say s Laplace transform x of t minus x of 0. That's what we said this derivative was equal to, equals Laplace transform of t. How do we take the Laplace transform of t? We just did a lot of examples of how to take Laplace transforms. We look at our table over here and we say, well, t to the nth power, it fits this mold. We take n factorial over s to the n plus 1. That's what this guy is equal to, where n is equal to 1. So what we have is 1 factorial on the top, s to the 1 plus 1 on the bottom. That is the Laplace transform of this. That's why we spent so much time learning how to take Laplace transforms so that you can do this. All right? Next, what we're going to do is we're going to simplify. S, Laplace transform. Now, instead of writing x of t all the time, I'm just going to write it as x. You need to remember that when you see an x, it's a function of time, minus x of 0. Notice this is an initial condition that's given to us in our problem statement, so you just substitute it in. Right? And on the right-hand side, it's going to be 1 on the top over s squared on the bottom. So you might look at this and say, well, geez, this doesn't help me any. How do I solve this differential equation here? I don't understand. Well, what we need to do is solve for Laplace transform. Get this on one side of the equal sign and see what we have. We can do that by putting a 2 on the other side. So this would be s times the Laplace transform of x is equal to 1 over s squared plus 2. All I've done is take the 2 and I've moved it over to the other side. And finally, I can divide by s to get this by itself. So that's going to leave me with the Laplace transform of x is equal to, if I divide by s, I'm going to get 1 over s cubed plus 2 over s. I've divided this term by s, I've divided this term by s, and then I'm done. So what I've figured out, okay, is that the Laplace transform of what I'm trying to find x of t. That's what all differential equations are trying to do. X of t is wrapped up in a derivative. In this case, it's wrapped up in a first derivative. We want to find out what x of t is, including how the initial conditions line up. But using this technique, we don't have the answer, but we don't know what x is, but we know what the Laplace transform of x is. And that's equal to this. So now if we just invert it back to the function of time, we will have our answer. So what we need to finally do to get where we're trying to go is we say that x as a function of time is equal to the inverse Laplace transform of this whole enchilada on the right-hand side, 1 over s cubed plus 2 over s. And we've already learned painstakingly that you can take this inverse transform and apply it to this guy, then you can separately apply it to this guy. So that's what we're going to work on now. How do we take the inverse transform of this, 1 over s cubed? We can go over this, over here, and see that it follows this guy, 1 over s to the nth, where n is 3. So t to the 3 minus 1 factorial. That's the answer for this guy. So it'll be t to the 3 minus 1 over 3 minus 1 factorial. That's the inverse transform of this. And then here we have 2 over s. And I think you probably realize that when we inverse transform 1 over s, we just get 1. So there's a 2 here, so we just do the 2, kind of comes out, inverse transform 1 over s and gives us 1. So x of t is t squared over, here we have 3 minus 1 is 2, 2 factorial is still 2, plus 2. This is the answer to the differential equation. T squared over 2 plus 2, that's the answer. Notice we don't have to apply any initial conditions anymore because we've already incorporated that information way up here whenever we did the Laplace transform and plugged it in. Normally when you solve a differential equation, by whatever means, you get the answer and then at the very end you apply the initial condition. When you're using the Laplace transform technique, we are incorporating the initial condition in our solution technique so we get to the answer and it's done. All right? So for this particular problem, it was very easy to get the answer. I think we talked before we started that we can integrate both sides. I asked you, what's the integral of t? And you said 1/2 t squared, or you should have said 1/2 t squared plus a constant. The answer we get is 1/2 t squared plus a constant. This constant comes directly from our constant of integration that you would have arrived at if you've done it the old-fashioned way or the other way by direct integration. Now in this particular case, because you can integrate both sides, doing a direct integration, probably pretty fast, maybe faster than this Laplace transform stuff. But I guarantee you that if you've studied enough differential equations, you'll know most of them can't be solved by integration like that. There's very complicated techniques to solve those guys. Now it boils down to a situation where we take the Laplace of both sides. This is going to be the general format. We take the Laplace of both sides, apply the initial condition, which comes about because of that. All right. Then we manipulate the equation and we solve for the Laplace transform of the function we care about. This is the step that we want to get to, that we can invert it back to our function of time. And now I hope you can see why we spent so much time just learning what a transform is, learning how to take the transform, learning how to take the inverse transform, practicing. Because if I throw you into a differential equation without that foundation, it's going to be tough. So that's really the power of Laplace transform method. You can transform that differential equation from something hard into something easier to solve. Notice that once we transformed it, it was just algebra to get down to effectively the answer, and then we had to transform it back, which we have some skills involved in that. So what we're going to do is wrap up this section, make sure you totally understand what we did here. Follow me on to the next section. I have several more problems where we're going to just use what we have already learned to solve more complicated types of differential equations. There's going to be a few hiccups along the way, there's going to be some algebra along the way, but the basic technique is exactly what we've outlined here. take the Laplace of both sides, manipulate, solve for the Laplace transform as a function of s, and then invert the answer. That's what we're doing in every one of these problems, and that's why it's applicable to so many different branches of math and science, because these differential equations, even these first-order differential equations like this, they pop up all the time in all branches of study. So make sure you understand this. Follow me on to the next section, where we'll continue learning how to use this Laplace transform to solve real problems.